Okay, we're back now with some solutions to the differentiation review problems that I introduced in the last video. Remember, the idea here is to work all these out by hand as much as possible and not use notes or calculators or other technology for this. When we're working these out before, I have checked them using a TI-84 and given some computer-generated graphs, I think for the most part using GeoGebra. And we'll study those things a little bit as we go along. The first problem, 1a, state the sum rule and prove it for derivatives. So it says the derivative of f of x plus g of x is f prime of x plus g prime of x. In other words, the derivative of the sum is the sum of the derivatives. So the function s of x is f of x plus g of x. We want to find that derivative. Well, that's s of x plus h minus s of x over h, a difference quotient, and then take the limit as h goes to 0 to make a derivative. That's the definition of a derivative. Now, we have that one calculus step and a whole bunch of algebra steps now, or, well, not a whole bunch, just several, and then one calculus step at the end. So s of x plus h means f of x plus h plus g of x plus h, and s of x is f of x plus g of x. Distribute the minus here, we get minus f of x minus g of x, and we can just drop the first parentheses here. Use the commutative property to switch the order of these two terms here, and then the associative property to group the first two and the last two and distribute the h to make this here. So it's like adding fractions but backwards. We already have a common denominator and go back this way or just reversing that. Now we actually use, so that was some algebra. Now we're going to have a couple of calculus steps. We're going to take the limit of the sum as the sum of the limits, like this, break it into two limits. And then the limit of each piece here turns out to be a derivative. The first one is f prime and the second one is g prime. Similarly, let's do the constant multiple rule. The derivative of a constant times f of x equals a constant times f prime of x. And I should say, probably should say for a constant, for any constant, c. And then this one is for any differential g. Okay. Okay, now, to prove that, it's pretty straightforward. The derivative of a constant times a function of x is to evaluate that function at x plus h minus evaluate the function at x, and then divide by h. Take the limit as h goes to 0. Both of these, this means a constant times that function. This is a constant times that function, so I can factor out that constant using the distributive property. I can use a property of limits that says if I have a constant times something here, I can probably get all the way out front of the limit sign, provided this limit exists, and it does because this function is differentiable, and so we get c times f prime. Product rule is a little harder. This was really nice. You know, the derivative of the sum is the sum of the derivatives. Derivative of a constant times the function is constant times the derivative function. But the product rule, the derivative product is not the product of the derivatives. The derivative of f of x times g of x is f of x times g prime of x plus g of x times f prime of x. The first times derivative of the second plus the second times derivative of the first. There are a couple of different orders you can write that because multiplication and addition are both commutative. Now remember that delta f, the change in the function f, is f of x plus h minus f of x. So f of x plus h is f of x plus whatever that change in f is. And similarly, delta g is g of x plus h minus g of x, so g of x plus h is g of x plus delta g. So when I do the derivative of f times g of x, then that's f times g of x plus h, which is f of x times g of x, f of x plus h times g of x plus h, minus f of x times g of x, all over h, and then take a limit as h goes to 0. Now I'm going to replace f of x plus h as f of x plus delta f. And I'm going to replace g of x plus h as g of x times delta g. Now I'm going to expand this multiplying the two binomials, basically by the distributive property. You may know it as FOIL. F of x times g of x is here. First times first. The outer product is f of x times delta g. The inner product is g of x times delta f. And the last times last is delta f times delta g. And then we still have minus f times g. Well, f times g at the end cancels with the f times g at the beginning. And then I want to think of this as the three fractions all over h, each one over h. So this is f of x delta g over h, g of x delta f over h, and f delta g over h all added together, and then take the limit. Notice that when you're writing this down, you should have equals here, not between the limit sign and the fraction, but out front, and then they should just be flowing down the problem here. Limit of the sum is the sum of the limits, so this is the limit of each of these pieces provided they exist. And here the f of x doesn't have anything to do with the h, so I can bring it out front. G of x does change as h changes. In fact, it goes to 0. Here g of x can be brought out front. And here I'm going to break this into two parts. One is the limit of delta f over h, and then the limit of delta g. Well, delta g goes to 0 and h goes to 0, so this has a form 0 with 0, but that's another way of just writing the derivative, right? It's the limit is h goes to 0 of delta g over h, or delta y over delta x, basically. Take that limit as delta x goes to 0, which is what this is, and that's g prime of x. Similarly, this one here is f prime of x. This is also f prime of x, but delta g goes to 0 as h goes to 0. So this last term goes away, and we're left with what we wanted, f of x times g prime of x plus g of x times f prime of x. We're going to use that sum in the next problem, actually. This one says find g of x is parentheses 5x minus 2 close parentheses to the fourth times parentheses 3x plus 5 close parentheses to the sixth. And I'm going to think of this after doing some substitutions as a product of power functions. So we're going to let u be the 5x minus 2, so that du over dx is 5. And let w be the 3x plus 5, so dw over dx is 3. So then the original function just becomes u to the fourth times w to the sixth. So g prime is the derivative with respect to x of u to the fourth w to the sixth. So I'm going to use the product rule. First, u to the fourth times the derivative of the second, derivative of w to the sixth, plus the w to the sixth, the second factor, times the derivative of the first, derivative of u to the fourth. Now this is just the power rule, so that's 6w to the fifth, but I made a substitution, so I have to multiply by the derivative of the w. Similarly, this is just 4x to the third. You bring the power down, subtract 1 from the power for power functions like that. But since the u and the x don't match, u is a function of x, I've done a substitution. I need to apply the substitution rule, or in other words, the chain rule, and multiply by the derivative of u. Okay, so derivative of w is 3. The derivative of u is 5. And then I can see what kind of things we have in common here. I see the 4 and the 5 is really a 2 squared times 5, so there's a 2 there. There's a 2 inside this 6, so there's a 2 in common here. They have a u in common. The smaller power there is one we're going to use, u to the third. They all have 5 w's in common too, so w to the fifth. So I'm going to factor that out using the distributive property. So when we divide that out, 6 divided by 2 is 3, times that other 3 is 9. U to the fourth divided by u cubed is u, and the w's cancel out. Plus, divide this one by that. 4 divided by 2 is 2, times the 5 is 10. This time the u's cancel out, and there's 1 w left over when I divide w to the sixth by w to the fifth. Substituting back in, u is 5x minus 2 here, and w is 3x plus 5 here. I distribute and get 45x minus 18 plus 30x plus 50. Combining like terms there, I get 75x plus 32 for the last factor, And then I went ahead now and substituted back in the u and w there on the first part. And so we see that g prime of x is 2 times parentheses 5x minus 2 to the third times parentheses 3x plus 5 close parentheses to the fifth times parentheses 5x plus 32 close parentheses. With that in factored form, it's real easy to see when g of x is 0. It's when each of these factors is equal to 0. 5x minus 2 is equal to 0 when x is 2/5. 3x minus 5 is equal to 0 when x is negative 5/3. And 75x plus 32 is equal to 0 when x is negative 32/75. And just to check this, remember you can check a derivative this way. Put the original function here in y1. Put the numerical derivative in y2. That's math 8 on a TI calculator, TI-84 calculator. And put your answer in y3. The tables for y2 and y3 should match. They do. So that indicates we did something well there. Here I use Graphmatica to graph the original graph in blue and the derivative in red, I believe. And you can see some of the things there. For example, both the original and the derivative are 0 at 2/5 and negative 5/3. 2/5 is 0.4 right there. Negative 5/3 is negative 1.6 repeating, which is somewhere about here. And then the derivative is equal to 0 also here at negative 32/75, which is right about here. Of course, that is going to be where this original function is at a maximum. This one over here at 2/5 turns out to be, actually turns out to be an inflection point of the derivative and a minimum of the original function. And this one over here, well, same thing for this one over here. Given that g of x equals secant of x times natural log of x, find the derivative and then evaluate at 1. And then maybe do some graphing and checking. Okay, so we'll use the product rule again. First times the derivative of the second. So secant of x times derivative of log of x plus log of x times derivative of secant of x. Derivative of log of x is 1 over x, log being natural logarithm of x. Derivative of secant x is secant x times tangent of x. So those are formulas that you definitely should have memorized. Let's see, they both have a secant of x. I'm going to factor that out. And so I'm left with secant x times parentheses 1 over x plus natural log of x times the tangent of x. Okay, moving on. Evaluate this at 1. Plug in 1 and see if we can figure out what's happening here with this. Let's see. 1 over 1 is 1. Natural log of 1 is 0. And tangent of 1 is something. And let's see. Oh, that's got an extra. Okay. But 0 times tangent of 1 is 0 plus 1 is 1. And so the answer is secant of 1, which is approximately this, if you would do it out in a calculator here. Secant of 1 is, of course, 1 over cosine of 1, which I did here in a calculator. Of course, always be sure you're in radian mode, always in calculus on your calculator. Here I put in, looks like I don't have the other calculator screen, but I did the same thing up here that I did up here. I just replaced y1 with the original function and y3 with my my derivative function here, and it looks like they are checking out. And once again, right there is the evaluating at 1. And here's what they look like. Because of the logarithm, this is only defined for positive x's and not all of them, because the secant of x is undefined some places too. So first of all, we're only positive x's, and then we also have vertical asymptotes where the secant of x is undefined. Let's see, where does that happen? That happens when cosine of x is 0 and that's going to happen at odd multiples of pi over 2. And so that's where you have all of these vertical asymptotes here. But in any event, you see this, the original function is the blue one, and the derivative is the red one there. Number 4, h of x is e to the power cosine of 5x to the 7th. Let's work this out. So here I'm going to have to end up using the chain rule twice. I'm going to have to do a series of 2 substitutions. So I'm going to let u be the power, cosine of 5x to the 7th. But I'm also going to think of w as being the 5x to the 7th. So the u is cosine of w. So with those substitutions, I'm just taking the derivative with respect of x of e to the u. Okay, that's simple. The derivative of e to the u is just e to the u, but then times the derivative of the u because of the chain rule. The u is cosine of w. Okay, that's not too bad. Derivative of cosine w is minus sine of w, but then times the derivative of w. The w is 5x to the 7th, so its derivative is 35x to the 6th. Now just substituting back in, I put the 35x to the 6th with the negative in the front, the sine of w, but w is 5x to the 7th, and I've got e to the u, which is the, well, it's the original function right there at the end. And then it says, find out when this is equal to 0. Well, e to any power is never 0. So first of all, when you have a bunch of things multiplied together and that equals 0, one of them has to be 0. So negative 35 can't be 0, but the x to the 6 could be 0 when x is 0. The e to the power can never be 0, but the sine of 5x to the 7th could be 0. So that's our sine of the w, right? So that's going to happen when the w, see, sine of x is 0 at integer multiples of pi. So n times pi such that n is an element of the set of integers. That little z is for integers. That means element of. Vertical line is such that. But that's for 5x to the 7th. So divide by 5 and take the 7th root. And we see that x is the 7th root of n times pi over 5, where n is any integer. And that does include the 0 as well, so I don't have to worry about that as well. Otherwise, I have to throw that in as well. And so those are the places where we have the derivative is undefined. No, not whether it's undefined. Where the derivative is 0. Actually, the derivative is actually defined everywhere. And so we look at this, and the original function is the blue one. Notice it has infinitely many maxima and minima, and they happen at these different places here. Again, there's a check, a check there. The check may not look like it's checking, but it actually does. Because what's happening with this, the derivative is oscillating faster and faster and faster, as is the original function, as we go out. And so because this thing's going up and down so wide, so much and so fast, that's why this table doesn't look very good if we check it very far from 0. It checks out pretty nicely, pretty close to 0 here, but then when we get further away, the check doesn't work as well. Because after all, this is a numerical derivative, symmetric difference quotient. Okay, let's do one more on this video, and we'll do the rest on the next one. So here we're given an implicit function, or not really a relation. It's not a function, but 8x cubed minus 4y squared minus 5xy equals -1. And here y is not a function of x is not a function of y, but we can still find dy over dx. So locally, we have a function, so this makes sense. We still have a tangent line, and that's the slope of it. So we can first of all, let's see what to do first. Find the derivative. So take the derivative with respect to x at both sides. The derivative of this constant on the right is 0. The derivative here is there's 3 terms, so they're going to get 3 derivatives added together. The derivative of the 8x cubed is 24x squared, and those are the same letter, so no chain rule is involved there. And next, the next term, again, just the power rule with the constant in front. Okay, so that's negative 8 y to the first power. But the y and the x are different. Y changes as x changes, so we need a chain rule to give us the dy over dx there. Now the last term here is going to be needs to be thought of as a product. I'm going to think of the first factor as negative 5x and the second as y. So it's the first factor, negative 5x, times the derivative of the second factor, derivative of y is dy over dx. Plus the second factor, y, times the derivative of the first. The derivative of negative 5x is negative 5. Okay, now what we want to do is solve for dy over dx, so we need to get those terms on one side and the others on the other. So I'm going to leave the 24x squared and the minus 5y on the left, but I'm going to add the opposite of these two to get them to the other side, so that gives me positive 5x dy over dx plus 8y dy over dx. I'm going to factor out the dy over dx, leaving parentheses 5x plus 8y for the coefficient, divide by that coefficient, and we get dy over dx is 24x squared minus 5y over this 5x plus 8y. Now notice this requires you to know both x and y to find the derivative at that point. And of course, for a lot of x's, there's more than one y. So first of all, notice that 1, 1 is actually on the curve. So plug in 1 for x and y here in the original and see that it works out. 1 here, 1 here, 1 here, 1 here. That's this. So that's 8 minus 4 minus 5 is negative 1, and the other side is supposed to be negative 1, so it checks. So 1, 1 is a point on the original curve, and that's the point of tangency as well, so it's going to be on the tangent line as well. Now what about the slope of the tangent line? Well, it's this derivative evaluated when xy equals 1, 1. So I'm putting 1 for the x's and 1 for the y's. And this turns out to be 24 minus 5 is 19 on the top. The bottom is 5 plus 8 is 13 on the bottom. So slope is 19/13. So point slope formula line is y equals the slope times parentheses x minus the x coordinate of the point plus the y coordinate of the point. Both of these are 1s, and the slope is 19/13, excuse me. And so that is the tangent line. We could distribute this out and put it in slope y-intercept form. We could even factor it out, make it slope x-intercept form, but really this is probably a better form for us in this context because it's clear that the point 1, 1 is on that tangent line. And when you graph it, sure enough, there it is on the tangent line, the point 1, 1. Here's the graph of the original relation, and here's the graph of the tangent line. And it does seem to check out, because if you look in here close to that point, the graph does look very much like the tangent line, very close by there. All right, I think that's probably enough for this video. Let's come back for the next one for looking at the rest of the solutions.